On our journey to the best basis, distinct eigenvalues make a basis. This is theorem 510 in the book. We have m eigenvectors with m distinct eigenvalues, possibly complex. If that's true, then the eigenvectors form a linearly independent list. So they become a basis for an m-dimensional subspace of the range. Super handy. Let's prove it. Suppose not. Suppose that this list of vectors is linearly dependent. We'll apply our linear dependence lemma with the twist that instead of solving for the largest index, we'll pick out the smallest index, so that vk is in the span of the preceding vectors. That's still the third vector from the video I did on the linear dependence lemma, just for those of you following along. But this is crazy. It leads to a contradiction with the fact that eigenvectors are non-zero. So vk is in the span of the others, so it's a linear combination of the other vectors. Hit it with the transformation. They're eigenvectors, and so they just get scaled. Linear transformations respect linear combinations, so it just distributes over the span. Here's the secret sauce. We multiply the top equation by lambda k and subtract. 0 is now a linear combination of the other v's. So when I subtract, I'm collecting the v's. So I have a lambda 1 v1, a lambda k v1, lambda 2 v2, lambda k v2, and so forth. But this list is linearly independent because we chose the smallest k that was dependent. So everything before then must be independent. By the definition of linear independence, all of the scalars must be zero. The only way for a product to equal zero is one of the terms has to be zero. But the difference is the lambdas aren't zero because they're distinct. So that means A1 has to be zero, A2 has to be zero, AK minus 1 has to be zero. Plug that into the definition of VK, and VK is the zero vector. That's crazy talk. Eigenvectors are non-zero. Thus, the original list must be linearly independent.